So you have seen now already a couple different algorithms for sorting a sequence of numbers. All of this from the standpoint of we just have a priority queue to work with. We have the operations insert and remove min, and we can sort a sequence by repeatedly calling inserting n times into our priority queue, and then repeatedly calling remove min n times from our priority queue, grabbing the minimum element and just placing it at the end of a list. So if we use an unsorted sequence to implement this, this is called selection sort, and the reason for that is the bottleneck of this algorithm, which runs in n squared time, is coming from calling remove min n times, repeatedly selecting the minimum. If we use a sorted sequence to implement a priority queue, this is called insertion sort, still runs in n squared time, called insertion sort because the bottleneck here is in calling the function insert. So now we have a more efficient implementation using a heap, which is appropriately called heap sort. And again, this is just that generic priority queue sort where we call insert n times and we call remove min n times. So because we're calling each of these operations n times, our total running time for heap sort is n log n. So we already have a more efficient sorting algorithm, at least most efficient that you've seen so far, which is using heap sort, using a heap to implement a priority queue and using that generic priority queue sort. So there's a few ways that we can implement a heap. We've seen that this is a binary tree and it satisfies those properties. Let me go back for a moment, that this is a binary tree storing keys at internal nodes, satisfies the heap order property and complete binary tree property. In order to implement this, we have a couple different ways that we could implement a binary tree, right? We can use a linked structure. So this is just nodes that's storing the position. It also stores the parent, kind of a reference to the parent and a reference to the left and the right child. Or one other implementation we have, and we talked about this when we went over trees, binary trees, we can also use a vector in order to implement a binary tree. And remember that this means that using a vector, we don't store anything at rank 0, but at all the other ranks, this is, we have always that the root is stored at rank 1, and then for anything else, it's ranked as based on if it's a left child or a right child of its parent. So a left child will have rank 2 times the rank of its parent. A right child will have rank 2 times the rank of its parent plus 1. So we have here rank 1, 2, 3, 4, 5. This would be rank 6, 7, rank 8, 9 if we had key store there, etc. So we don't actually have to store links between nodes because this is inherent based on what rank it has, or any leaf nodes. And this gives a nice way that we have immediately the last node is at rank n. So we know where our next node should be as well too. So this gives us an in-place heap sort if we were to use this in order to implement our heap, and we used our generic priority queue implementation in that way. So we were given a vector. An in-place sorting algorithm wouldn't create any additional data structures. It would work directly on the data structure that we're given. So an in-place heap sort would implement our heap using the same vector that we were given. Okay. The reason why this would be an efficient implementation for a heap, if you remember before I mentioned that the total number of cells that we would need in our array would be, so this is the space required, would be big O of 2 to the power of the height of our tree. And in general, this isn't very good. We can't bound this in any way. So for an arbitrary tree, we might have a lot of empty cells in here, which are kind of taking up space so that we don't really need them. But because of how we constructed our heap, because this is a complete binary tree, we know that the height of this tree is bounded logarithmically. So this is big O of 2 to our height is big O of log n, so log base 2 of n, which is 2 to the power of log base 2 of n is just n. So in this case, we do have an efficient implementation of a binary tree of our heap specifically, because we know that this is a complete binary tree, because we know that the height is bounded. Okay, so this already gives an in-place implementation of heap sort as well. And you might be wondering also, how else could we improve heap sort? So for example, we call insert item n times, which takes a total runtime of n log n. Each call to insert item takes log n. But when we're using a heap in order to sort a sequence of elements, we know ahead of time what all of those elements are that we're going to put in our heap. And there's a little bit more efficient way of going about that rather than calling insert item n times, and this is called bottom-up heap construction. So if we know in advance what all of the keys are that are going to be in our heap, then rather than calling insert item n times, we can build up a heap recursively. So this is called bottom-up heap construction. And the idea is that in order to do this recursively, this is, we'll start off where we have two valid heaps already. So we have like a left heap and a right heap. And we'll join this into one larger heap with some element here, which will be our root. So the idea is we know all of our keys in advance. We can start off by building a complete binary tree, and then from there recursively turn this into a valid heap. So let me show you an example of this first. So in order to give kind of a recursive solution to this, we need a way to, if we already have a valid left heap, so this is our valid left heap, and this is our valid right heap, how would we turn this into one large heap here? Right? So we have some root element. We can make this the left child, this the right child. And if we had already, this was a heap and this was an okay heap, how do we make sure that by adding this new root node, we maintain that we still have a valid heap? So let me show that first, and then we'll go into an example. So let's say we have already these two heaps. This is our first heap, 1, and this is our second heap, 2. And we have some other key, k. So in this case, let's say our key k is the key 7. So how would we turn this into a valid heap? We want to combine heap 1 and heap 2 and the key 7 all into one large heap. So we have to maintain the complete binary tree property and the heap order property as well. Well, we know the left and the right heap are already valid heaps, so this is kind of our left heap, that same heap 1 what I showed up above, and our right heap. And we're joining them together using that key as our root of this new larger tree. And since we know everything in the left subtree and the right subtree satisfy the heap order property because they started off as heaps already, then we're just going to have to perform the down heap algorithm in order to make sure that by adding this new node, we didn't violate the heap order property. We know we still have a complete binary tree, so we just need to check now that we didn't violate the heap order property. So we're going to compare this node, the value of this node, to the value of its children, the keys at its children. So with our heap, again, we're always talking about a min heap here. We want any given node to have a smaller value than its children. So if it doesn't, we're going to take whichever child is smallest and swap with it. So in this case, 2 is smaller than 7, so we're going to swap these two. And then we check again. We fixed it locally. Did we kind of propagate this heap order violation downward? So once we place here 2 and here 7, we check again, did we violate the heap order property, which we did. 7 is larger than its children, so we're going to swap with the smallest child. So we'll swap 7 and 4. So this is how we get the low heap. So this is just an idea of how we can use this in order to recursively build up a heap. And the idea is if we already have 2 good heaps, we can build an even larger heap by combining them with another key and build a larger heap that way. So we'll see, how do we actually get these keys? Where is this coming from? Let's do an example next. So let's say we're given the sequence already, 10, 7, 8, this entire thing. So the idea is we're going to fill in first a complete binary tree. So let me write in here, we've got here 10, 7, 8, we're just going to fill this from the top to the bottom, each level from left to right. 8, 25, 5, 11, 27, and then the rest of them are already filled in here. So I didn't write these in initially because these are just kind of placeholders for the moment. We're just going to evaluate this level by level. So this is our base case now. So we've got a valid heap here, 16, and its children, which are just external nodes. We've got a valid heap here, a valid heap here, and so forth. We've got 1, 2, 3, 4, 5, 6, 7, 8 valid heaps to work with. Now that we have a valid heap here on the left and a valid heap here on the right, we're going to create one larger heap that has both of them, and it also has the key 25. So how we got that key 25, this was just kind of initially when we were given this sequence, we filled this from kind of from left to right, just starting at the top level and filling each level from left to right as well. So, but these are just kind of placeholders initially. So we want to construct one large heap containing everything, and how we do this is by reducing it to, in our base case, we have just these really small heaps, and we merge them into to create a larger heap. Okay, so for this one, let's do this one. So we're merging the heap on the left and the heap on the right with the key 25. We just have to use our down heap algorithm now to make sure that we satisfy the heap order property. So we're going to swap 25 with its smallest child. So I'm going to show you the result of that in the next slide, but we're going to swap 25 and 15. Now when we get to the next one, okay, we have a valid heap on the left, which is just 4, valid heap on the right, which is just 12, and we're going to merge it into a larger heap, which includes 5 also. Now we check if by adding this new node as our root, did we violate the heap order property, which we did, so we're going to swap it with the smallest child. Then again over here, so we've got, this is our valid left heap, our valid right heap. We joined it with 11. Did we violate the heap order property? Yes. So we're going to swap it with its smallest child. And then again on the right. So our valid left heap, our valid right heap, and we're going to use them to build kind of an even larger heap, which includes 27. And in doing so, did we violate the heap order property? We did, so we're going to swap this with the smallest child here. So I'm going to show the result of that on the next slide. Okay, and let me fill in here our placeholders, what we had here, 7, 8, and 10, just kind of carry it over from the previous slide. So this is already the result of after swapping these values, what we get. So now we have, this is one large valid heap. This is another valid heap. Each one of these is a valid heap. So we went from having, initially we had 8 heaps of size 1. Now we have 4 heaps of size 3. Okay, so let's continue. So now that we have, this is a valid heap, and this is a valid heap, left and a right heap, we want to build an even larger heap, which also includes the value 7. So in doing so, once we added 7 to the root, we have to check, did we violate the heap order property? Which in this case we did. So we're going to swap 7 with its smallest child, which is 4. And then if we still violated the heap order property, which we did, we'll swap with its smallest child, which in this case is 5. So 7 bubbles down to this location, and everything else that it swaps with moves up 1 position. So now we have one large heap containing all of those elements. And this is a complete binary tree that satisfies the heap order property as well. So the same thing on the right side. We have one valid heap on the left, one valid heap on the right, and we merge this together with an element 8. So 8 was just a placeholder there based on in what order it appeared in our sequence. And we're going to turn this into one larger heap by performing the down heap algorithm on 8. So we just want to make sure that we didn't violate the heap order property, which in this case we did. So we're going to swap 8 with 6 because 6 is the smallest child. And then once we put 8 here, again, did we violate the heap order property? No, we're okay because once we place 8 there, it's less than or equal to the keys of its children. So with a min heap, we always want to keep the smallest keys on top. Okay, so now that we have finally our left large heap and our right large heap, we want to turn this into an even larger heap which contains 10 as well. So we already know this satisfies the heap order property and is a complete binary tree, both the left heap and the right heap. And by combining them in this way, we still have a complete binary tree. We just have to make sure we don't violate the heap order property. So if we do, we down heap bubble. So we're going to take 10, and because it's larger than its children, than even one of them, we're going to swap it with the smallest child, which is 4. So 10 goes here, and 4 will go here. Then we check again. Did we violate the heap order property? We did, because it has a value larger than one of its children. So we're going to swap it with whichever child has the smallest value. So between 15 and 5, we swap with 5. So 5 is going to go here, 10 goes here, and then we again check, did we violate the heap order property? So again, we did. So we're going to swap 10 with 7. So this is our resulting heap. So this bottom-up heap construction works by, we're given a sequence, we kind of fill in that sequence from, just as placeholders, we create a complete binary tree using that sequence. And then we recursively build up larger and larger sized heaps. So it might not be immediately clear why this is more efficient than just calling insert item n times. So let's see how we can evaluate this. So we're going to look at what happens when we have to down heap, because we can build a complete binary tree just by, in linear time, just by filling in from left to right those placeholder values. And then the bottleneck of our problem in terms of runtime is in those swap operations when we have to down heap. So every time we merge heaps, we have to potentially down heap all the way down the tree. So we're just going to visualize the worst case runtime. So in the worst case, our down heap will have to go from that root element, say we're merging this left heap and this right heap together with this root. In the worst case, this has to down heap all the way down our tree. So we're going to visualize that in each instance. Let's suppose that in the worst case, we had to swap this node. It followed some path from the root all the way down. Now maybe it actually went to the left and then to the right or something, but just doesn't matter which way it went, because we only care about how many swaps had to occur. So whether we swapped this root node to the left and then to the right and then to the right and then to the left, or if we went to the right and then the right and then the right all the way down, or maybe to the right and then to the left, no matter which direction we went, in the worst case, we go from the top all the way to the bottom, right? So no matter which way we visualize this, going from the top all the way to the bottom, we still have the same number of swaps that would occur in the worst case. So we're going to choose to visualize this as every node. Let's imagine a proxy path which goes first to the right and then all the way to the left. So first to the right and then all the way to the left. So each node goes to the right and then all the way to the left. This is a proxy path of when we use that node in order to merge together two heaps, where it would have to down heap bubble. So this isn't the exact path that it would take. This is, we're just going to visualize it this way because we don't care about which path it takes, we just care about how many swaps will occur, and the same number of swaps will occur no matter which path it is. So when we visualize it this way, we can see that every node is traversed by at most 2 proxy paths, meaning that that position would be swapped at most 2 times. So this is coming from, let's say for this node, when is this swapped? As a part of its own proxy path and also as a part of its parent's proxy path. So each node only takes part in at most 2 proxy paths, and we have n nodes. So that means we have big O of 2n swaps that occur, which is big O of n. So our bottom-up heap construction runs in total linear time. So we have, if we were to just call n calls to insert item, this is the other way that we had of constructing a heap. This costs n log n. Much better, if we can, to use bottom-up heap construction. Now the caveat here is that we have to already know in advance what all the keys are that we want to include in our heap. But if we use bottom-up heap construction, our total runtime is linear. So this is more efficient implementation. So does this improve our heap sort at all? Kind of, it does. It'll improve the first phase of heap sort when we're actually constructing a heap. So we can construct a heap in linear time, but when we're using heap sort, there's a second phase to this, which is first build the heap, and then in our second phase, we repeatedly remove the minimum. And that second phase doesn't improve at all. N calls to remove min, when each call to remove min costs log n, the second phase will cost a total of big O n log n time. So we kind of improve heap sort, but this is only the first phase of heap sort. So heap sort will still be n log n, but we can at least construct the heap faster. Okay, if you have any questions, please post on Piazza and let me know.